Okay, so for section 3.5, we are looking at absolute maxes and mins instead of local. So instead of looking at a specific interval relative to the y values around it, we're looking globally. So these are called global or absolute maxes and mins instead of local or relative. And so we are going to do that. These are closed things that are on closed intervals. That's when you look for absolute maxes and mins here, or we're looking at absolute maxes and mins on closed intervals. So if C is in the domain of F, and for all X in the domain of F, we have F of X is less than or equal to F of C, then F of C is an absolute maximum. And then if it's greater than or equal to all of the function values, then it's an absolute. If all the function values are greater than or equal to it, then it is an absolute minimum. Okay, so that's a lot of words. It was hard for me to even talk through, but let's look at them and see if we can figure this out. So looking at these graphs for a minute, let's look for the absolute maximums on all of them first. So this is the highest point on the graph total. That's the absolute max. That happens at the ordered pair 2, 2. Here, this is our absolute max at what, -2, 3. We have an absolute max right here. I don't know why I'm doing that like that. I have space next to this. Absolute max here is that ordered pair at -1, +2. And here's our absolute max that appears to be at 0, 3. Okay, so they're just the tallest point on the graph, period, the whole graph, the highest y value achieved on the whole graph. And then absolute minimum, the opposite thing. You're looking for the lowest value achieved in the whole graph. There's only going to be one. If you were talking about relative minimums, there could be a bunch, but when you're talking about an absolute minimum, it's absolutely the lowest point. So this is our lowest point here. That's the absolute min. That's at -3, -3. Over here, like what I was saying, like this is a relative min, but it is not the absolute. This is the absolute min here at -4, -2. On this one, it's right here, the lowest point on the graph, period. That is 1, -2. On this one, we have this guy right here. So this last graph, it has no local minimum, but it does have this absolute minimum at 4, -2. The first one also doesn't have a local min at all, but it does have this absolute min. This has a local min and this absolute min. This is a local min, but it's also a global one or absolute. Okay. So hopefully that makes some sense. If you look at all of these, where do those happen? Where do the absolute mins or maxes happen? Well, it looks like they happen at what would be relative extrema too. So where the derivative is 0 or undefined, so those would be critical values. But it could also happen at the endpoints. Here's the difference: is we're on this closed interval. Oops, we're on this closed interval, so these endpoints do matter. So these absolute extrema, they can happen at any critical values or at the endpoints of the interval. Critical values, remember, is where f prime is 0 or undefined. So at critical values or at the endpoints of the interval. Of the closed interval, that's the difference here. Okay, so let's try this. What we're going to do is, we're going to talk about the definition. Finding them, I'm going to tell you how to do this. To find them, you're going to find the critical values again on that closed interval. So we're looking for where f prime of x is 0 or where f prime of x does not exist. Plug the values in from step 1 and the endpoint. So these are your critical values and the endpoints into the original function. You're looking for where that original function, so basically we're finding the only places it can happen, and then we're going to plug them in to see which one actually does it. So the largest value is the absolute maximum, the smallest value is the absolute minimum. So we're going to take a derivative to find the critical values, but then we're not going to use it after that. So that's what makes this different than finding local extrema. So when you're finding absolute extremes, you're going to take a derivative to find a critical value. So f prime of x is here 2x minus 8. We're on this closed interval. This has no, this is continuous or defined everywhere. So we have no discontinuities or no places where the derivative doesn't exist everywhere. But where does it equal 0? So 2x minus 8, 8 equals 2x, x equals 4. That's our critical value. So instead of doing a number line, because we're on this closed interval, we know that the only places this thing is going to have the only places it could have these absolute extrema possible for absolute extrema are critical values and the endpoints. So that's what we're going to do. We're just going to plug them in. So plug those into your original function, those values into f. So we have f of the first endpoint, that's 0, f of our critical value, that's 4, and then f of 5, our other endpoint, and then the CV. So f of 0 going all the way back to the original function, that's 0 squared minus 8 times 0, which is going to be 0. Plug in 4, we get 4 squared minus 8 times 4, that's 16 minus 32, so negative 16. Plug in 5, 5 squared is 25 minus 8 times 5, which is 40, that's negative 15. So the absolute maximum happens here, that's the biggest value. The largest value is the absolute maximum, and the smallest value is the absolute minimum. So this is the absolute minimum. So to give the answer in a formal way, this has an absolute max at that ordered pair, which would be 0, 0, and an absolute min at the ordered pair 4, negative 16. So the only places it's possible for this thing to have absolute extrema would be at those critical values where the derivative is 0 or undefined, or at the endpoints of the interval. So we're going to plug all of those things into the original function. Whichever one is biggest is where the function is the biggest. Whichever one is the smallest is where the function is the smallest. All right, let's do that again for number 2. We'll find the derivative first so that we can find our critical values. That's 6x minus 12. We have this closed interval. This is defined everywhere. So we're going to find our critical values just by setting it equal to 0. So 12 equals 6x. So x equals 2. That's 12 divided by 6 is 2. So we have this. This is our critical value. So we are going to take then, we're going to plug in our critical values and our endpoints into f. So we are looking at f of first endpoint, which is 0, f of the critical value, and then f of the other endpoint. So this is the end, the CV, and if you have more than one critical value in the interval, use it. So f of 0 would be 0 minus 0, so it's 0. F of 2 is going to be 3 times 4 minus 12 times 2. What's that? 12 minus 24, so negative 12. F of 4 is going to be 3 times 4 squared, which is 16, minus, I can't do this in my head, 12 times 16. That's what, 48 minus, I don't know what 12 times 16 is. 3 times 16 minus 12 times 16. So it would be whatever 9 times 16 is, 144. Negative 144. So we have here at 0, this is our absolute max, that's the biggest. And the smallest is here at 144, that's the absolute min. So we have an absolute max, I was supposed to be using purple, absolute max at 0, 0 again, and then an absolute min at 4, negative 144. So this doesn't happen at that critical value. It looks, you have 0, 0, and then 2, negative 12, and then 4, negative 144. So it's doing something like this, except the derivative is 0 there. So maybe like this or something. That's what's giving us that global maximum down here, a global minimum down here, a global max here, and some critical value here that is actually the absolute minimum. Okay. Keeping on going here. Let's see, what do we have? Those, and then these, y'all will do on your own. Oh, we'll do these word problems. Okay. Let's go back to number 3 then. Let's start there. We're going to take a derivative again to find a critical value. So f prime of x here, that 8 is 0, then this would be negative 3x squared. This is defined everywhere, so we don't have any places to worry about except the zeros. So we're going to set this equal to 0 and solve. So x squared is 0, so x is 0. And that's in our interval, so that's good. That's our critical value. So we are going to take this, we're going to plug into f. We're going to plug CV and ends into f and check them. So f of negative 1, f of our critical value, and then f of 3. So this is an end and an end and a CV. So if you plug into f, you have 8 minus negative 1 cubed. So that would be 8 plus 1, so that's 9. And then if you plug it in 0, we get 8 minus 0, so that's 8. If you plug in 3, you get 8 minus 3 cubed. 3 times 3 is 9 times 3 is 27. So negative 20, negative 19. So then we have our absolute minimum here and our absolute maximum here. So absolute max at negative 1, 9, and absolute min at 3, negative 19. All right. Number 4, doing the same thing again, take a derivative, find the critical values, or where the derivative is undefined, plug those and the endpoints into f to see which is biggest and which is smallest for absolute extrema. So f prime of x here, this would be 8x squared minus 2x. Exponent, that's not an 8. 2 times 3 is 6. Exponent down front, decrease it by 1, and then do that again. All right, this is defined everywhere, so you don't need to worry about discontinuities, places where the derivative is undefined. So we have then 0 equals 6x squared minus 2x. I'm going to factor 2x out of that, so I have 3x minus 1. So 2x equals 0. Set each factor equal to 0, so x equals a third plus 1 divided by 3, and then divide by 2 over here, so x equals 0. Those are our critical values. You're going to put them, you're going to plug them into f with those endpoints. Plug CVs and ends into f for absolute extreme. Okay, so we have here f of 0, f of 1/3. This is an end and a critical value. That's kind of cool. F of 0, f of 1/3, f of 2. This is an end. This is a CV. Then you plug these in. 2 times 0 cubed minus 0 squared, that's 0. You plug in a third. You're going to trust me on this. You get negative 127. You have 2 times 1 over 27 minus 1/9. So negative 1 over 27. And then when you plug in 2, that's 2 times 8 minus 4, so 60 minus 4 is 12. So here is the absolute min, the lowest value, and here is the absolute max. So as ordered pairs, we have an absolute max at 2, 12, and an absolute min at 1/3, negative 1 over 27. Okay, continuing on, again, doing the same thing. F prime of x equals here 3x squared minus 6x minus 24. Take a derivative. That's defined everywhere. So we're going to set it equal to 0 and try to factor. No, it's 7. I factor by guessing and checking. Hopefully that'll work here. Um, 24 is, oh, all of those are divisible by 3. How about I start there? So we have 0 equals x squared minus 2x minus 12. That's going to be easier to factor. There's going to be a 3 and a 4. Oh, nope, nope, nope. I need 2. Oh, 24 divided by 3 is 8, y'all. I struggle sometimes. So 4 and 2, we need minus 4 plus 2. Use quadratic formula if you need to. Absolute b plus or minus the square root of b squared minus 4ac all over 2a. First works outer, inner. That's good. Okay. So then x is negative 2. Set each factor equal to 0. So x is negative 2 or x is equal to 4. Those are our critical values. Both of them are in our interval, so we're going to need to plug them all in. So check CVs and ins in F. So we're going to have F of negative 3, F of negative 2. 4 is not in there, so we don't need to worry about that one. F of 3 are other ends. So these are ends, and this is the critical value. Again, we don't need to do this one because it's not in this interval. All right. So when we plug in negative 3 to the original function, you have negative 3 cubed minus 3 times negative 3 squared minus 24 times negative 3. This is 18. When you plug in negative 2, you get 28. When you plug in 3, you get negative 72. So this negative 72 is the absolute min, and 28 is the absolute max. Y'all check those to make sure that those numbers make sense, but that's what I have worked out. So we have an absolute max at negative 228, and an absolute min happens at 3, negative 72. All right. So we will get a place here where we have an undefined spot on the derivative. So let's work this one too. F prime of x would be 4. This is equal to 9 times x to the negative 1. So this would be minus 9 times x to the negative 2. Exponent down front decreases by 1. If you wanted to rewrite this, this would be 4 minus 9 over x squared. So this is f prime of x. This, we want to recognize that this is undefined. Pink. This is undefined at x equals 0, because that would make us divide by 0 here, and we don't want to do that. And then if we want to set the whole thing equal to 0, 0 equals 4 minus 9x squared. So 9.
My headphones just died, but hopefully y'all will still be able to hear me on my iPad. So 9 over x squared equals 4. Add 9 divided by x squared to both sides. Here I'm going to move up here to work. Multiply both sides by x squared. So 9 equals 4x squared. Divide by 4. So 9 over 4 equals x squared, and then take a square root. So you're looking at this plus or minus here. That the square root of 9/4 is 3/2. So you're looking at plus or minus 3/2. So we have critical values at 0, negative 3/2, and 3/2. We do not need to worry about either of these because they're not in our interval. Our interval is from 1 to 3, so we're not going to worry about 0 or negative 3/2. Okay, but then we are going to check these. Check CVs on interval and the endpoints. So we're looking at f of 1, f of 3/2, and f of 3. And when you plug those things in to f, the original, this is 13, this one is 12, and this one is 15. So this is your absolute max. This is the absolute max. And this is the absolute min. So we have an absolute maximum at 315 and an absolute min at 3/2, 12. Okay, so on these practice problems, 1, 2, 3, those are going to be similar to what we just did. So y'all give those a shot. I'm going to try to walk you through 4 and 5. On number 4, we're looking at the revenue from a sale of X units of a product is given by this function, R of X. This is in thousands of dollars where X is between 0 and 250. So this closed interval is telling us that we might, that we need to be aware of that. How many units should be sold to maximize the revenue? So we're maximizing on a closed interval. That means we're going to do absolute extrema. Okay, so we are going to take a derivative, find the critical values, and then compare them with the function values at the endpoints. So r prime of x here is going to be 12 minus, so the derivative of that's just 12, and then this would be an exponent down front, decrease it by 1, so negative 0.08 x. This is defined everywhere, so you don't have any discontinuities. So then we are looking just where it's equal to 0 for the critical values. So 0 equals 12 minus 0.08x. 0.08x equals 12. Divide by 0.08, x equals 150. So then we're going to look at these, compare f at CVs and ends. So we are going to look at R in this case, R of 0, R of 150, and R of 250. So the two endpoints and our critical value. When you do this, this is 12 times 0 minus 0.04 times 0 squared. When you do this, you get 0. When you plug in 150, I got 900. And when I plugged in 250, that's a 2. When I plugged in 250, I got 500. So we have an absolute min and we have an absolute max. And that makes some sense that if they haven't sold any units, then they have no revenue. If we were talking about profit here, that would probably be negative, because selling no things but having made stuff means that you would probably, or bought stuff or whatever, means you haven't made a profit. But revenue here is just money coming in. So the fact you haven't sold anything means you don't have money coming in. And then their revenue after they sell, they want to sell 150 things to maximize that revenue. So if they go beyond that, they are decreasing their revenue. All right, so we have an absolute, so they should sell 150 items or units to maximize revenue. All right, and then lastly, let's do this. This is going to be a profit one. So a manufacturer of telescopes has determined that the revenue from the production and sale of X telescopes is R of X equals 140X minus 0.5X squared dollars. Cost is given by that function. Find the level of production that will maximize the profit on a closed interval. Maximize on closed interval, do absolute extrema. Okay, so we want to find the derivative, but we need to find the profit function first. Maximizing profit. So we need to find P. Remember, P is the profit is the revenue minus cost. So in this case, P of X is going to be 140X minus 0.5X squared. Minus the cost. I'm going to distribute a negative to those things. So minus X squared minus 20X minus 1050. Combining like terms there. 140 and minus 20 would be 120x. 0.5 minus 1 would be 1.5. And then minus 1050 still. So this is your profit function. So if we are trying to maximize profits, we're going to take a derivative. So that would be 120 minus 3x minus 0. This is defined everywhere, so we don't need to worry about that, but we will set it equal to 0. So 3x equals 120. So X is 40. And that's our critical value. So now we're going to look at those with our ends. So compare P at CVs and ends. So we're looking at P of 0, P of 40, and P of 70. Those are our ends that were given to us in the problem. End, CV. So when you plug into the original profit function, this is where we're plugging in. You plug in 0, you get negative 1050. When you plug in 40 to that thing, I got 1350. And when I plugged in 70, I got 0. So again, this makes sense. Their profit when they've sold nothing is negative because they had some cost in doing that. They maximize their profit at 40 units sold. So they maximize profit when they sell 40 units. When they produce and sell 40 units. Okay. Well, that is 3.5. You guys let me know if you have any questions, and I would be happy to help you. Thank you.